Hi all, today we discuss the hyperspace again. We have already seen that what is the definition of hyperspace in finite dimensional case. If we use a finite dimensional vector space, then say n dimensional, then any subspace of dimension n minus 1 is called a hyperspace in finite dimensional case. Uh, in this session, we will discuss what is the definition of hyperspace in arbitrary space. First, we define maximal subspace. If n is a subspace of V, it's a proper subspace of V. So n is a proper subspace of V, and suppose we have an element alpha such that the span of n union singleton set alpha, okay, is equal to V. That means if W is a subspace of V which contains n, then either W equal to n or W equal to V. Okay, so uh, this can be written as n is a, suppose there exists a subspace W in between V and n, then you can get this W is same as this n, or this W is same as V. Okay, or you can say that the span of n union any element. If you choose any element alpha not in n, that means alpha comes out, from the outside of this n. Then consider the span of n union alpha. So this is always a subspace. If you have if you name it as W, then this W definitely is greater than this n, or it contains n properly, because this W contains an alpha which is not in n. Then this is always a subspace of V. So we have this W as V. That means span of this is equal to V. So this is another way of saying this type of subspaces. Or you can conclude the definition of the maximal subspace with these two conditions. N is a proper subspace of V, and if W is any subspace in between V and n, then that subspace coincides with this n, or it will be the whole space. If this whole, then this n is called the maximal proper subspace. If V is a vector space, a hyperspace is defined to be the maximal proper subspace. Okay, a subspace with these properties are called hyperspaces. Now we'll prove that if you consider any non-zero linear functional, then the null space of that linear function is always a hyperspace in V. And converse is also true. If you consider any hyperspace, then that can be considered as a null space of some linear functionals. In case of finite dimensional vector space or infinite dimensional vector space, that will be true for an arbitrary vector space. So we start with this theorem. Suppose we have a vector space V and f is a non-zero linear functional. Okay, so this belongs to V star and f is not equal to 0. So this is a non-zero linear function. We will prove that this null space of n is the null space of f. Okay, that means this consists of all vectors of null space of f, means that if all alpha belongs to V, such that f of alpha equals 0. So this is the null space. So n is the null space of, if n is the null space of f, we will prove that this n is maximal. How will you prove this n is maximal? We choose an alpha from the outside of this n, and we will prove that the span of n union singleton set alpha will be the whole space V. Okay, now we'll start with an alpha not in n, and we'll prove this. Okay, if alpha not in n, then you can say that I'll call it as nf, is the null space of f. Then the subspace spanned by n union alpha, consisting of the vectors gamma plus c alpha, where gamma belongs to n and nf, and c belongs to f. C belongs to capital F. So this is the arbitrary element. These are the arbitrary elements of span of n union alpha. We'll prove that this is V. Okay, so that means any beta belongs to this V can be written as this form. So that is our this is always a subset. One inclusion is always there. So we need to prove the reverse inclusion. That means every element of beta can be written as element of n union alpha. That means gamma plus C alpha. So we start with beta belongs to V. Now we define C is equal to f of beta by f of alpha. This term is this quotient is defined because these are all elements of f, but f alpha not equal to 0 because alpha comes from the outside of this nf, the null space. Therefore, f alpha never be 0. And then C is defined. C is a non-zero scalar in C is a scalar in f. So this is always an element of f. Okay. Now we will consider this gamma is equal to beta minus. Now we'll consider beta, not gamma. We consider the quantity this beta minus C alpha. Okay, so beta minus C alpha. So corresponding to each beta, we define C. Using this beta and C, define a new element beta minus C alpha because alpha is given here. Then what is f of I put it as gamma for some say gamma, that is f of gamma is nothing but f of beta minus C alpha, that is equal to f of beta minus C times f of alpha, but C is chosen in such a way that C is equal to f of B minus f of A. So this will be f of beta minus C is nothing but f of beta by f of alpha times f of alpha. Since f alpha is non-zero, you can cancel this, then this will be 0. So this shows that this element is an element of n alpha. I put it as gamma. Then what is beta? Any beta can be written as gamma plus C alpha. So this shows that this beta belongs to V implies beta belongs to the subspace spanned by n union singleton set alpha. So that shows that n alpha is a hyperspace. Now we prove that every hyperspace is a null space of some linear functional. So we start with a hyperspace. Let n is a hyperspace. So here we start with a hyperspace, and we'll prove that this n is a null space of some linear functional. So starting with this n, it's a hyperspace. Since it is hyperspace, you can find an alpha such that n union alpha, the span of n union alpha is equal to V, where this alpha is not in n. Okay, alpha is not in n. So corresponding to this n, we will find a linear transformation. Okay, linear functional as well. In fact, so this is a the definition of the hyperspace. Then if you have any any beta belongs to V, then this beta can be written as an element of n plus C alpha, because this beta belongs to V and V is this one. Then gamma is an element of this n, and this alpha belongs to singleton set alpha. Okay, now every element beta can be written in this manner, and we'll show that this C is unique, because if this beta has another expression like this, say gamma prime plus C prime alpha, then you can easily equate this gamma plus C alpha will be coincided with gamma prime with C prime alpha. Okay, so this implies gamma minus gamma prime plus C minus C prime alpha equal to 0. Okay, then this implies that gamma minus gamma prime equal to c prime minus c times alpha. So this implies that this gamma minus gamma prime is always an element of n. If this is the expression, then the right side is an element of n. Okay, that is a contradiction because alpha is not. That means this c prime minus c times alpha equal to 0. Not 0. This belongs to n. This is a contradiction if this c prime minus c is non-zero. Clear? Because if this is non-zero, you can say that alpha is an element of n by dividing with this. So that will be a contradiction because we start with alpha which is not in this n. So this implies that c prime minus c equal to 0. Consequently, if c prime c is equal to c prime. So when you write this beta in such a way that beta is equal to gamma plus c alpha and beta is equal to gamma prime plus c prime alpha, that means if same beta has more than one expression, then that c and c prime and gamma prime are coincident. That means there exists only one, this beta has unique expression when you represent it as a it is an element of n plus c times alpha. So this would enable us to define a new map. Say f from v to this f defined by f of beta is defined to be the scalar. Okay, so any beta belongs to v, beta can be written as gamma plus c alpha, and the c is unique. Then define f of beta is equal to c. Okay, clearly this is a linear transformation because whenever you write f of some k times beta 1 plus beta 2, then that will be f of this k times beta 1 can be written as gamma 1 plus c1 alpha 1 alpha plus this beta 2 can be written as gamma 2 plus c2 alpha. Okay, so this is same as f of, we can write it as k times gamma 1 plus gamma 2, okay, plus k times c1 alpha plus c2 k times c1 alpha plus c2 times c is k times c1 plus c2 times alpha. So this implies the definition of this is k times c1 plus c2. Okay, so this is same as k times f of this beta 1 plus f of beta 2. So this shows that this f is a linear transformation. So we have corresponding to this each n belongs to for corresponding to any hyperspace n, there should exist f, okay, such that f of beta is equal to 0. We define this f in this manner. Now what is the null space of this? Null space of f. Null space of f is defined as set of all elements of v. I'll write it as gamma plus c alpha, such that f of this quantity is equal to gamma plus c alpha is equal to 0. That is set of all gamma plus c alpha such that f of gamma plus c alpha is c equal to 0. That means set of all gamma belongs to n. So this is the definition of the null space. So this n is nothing but nf. So every hyperspace is a null space of some non-zero linear functional. This proves the theorem.